Okay, so we are slowly arriving here. I still give everybody a minute. Let me see participants list. Okay, great. Okay, so welcome back, everybody. First, let's start with the good news. We finally managed to be live on YouTube. So, especially for the next teams, it might be of interest for tomorrow and the day after tomorrow. Now, finally, we know how the little things we need to take care of to make this happen. Great. Yeah, you just heard that the recording started, and so we can go on with the next session. So now we will have some two presentations and a lab presentation. I don't know, Sila, I see that you're there. You want to say something about the next two presentations? Yeah, you're looking for your microphone. Okay. Anyway, let me say that if during these presentations, the presentations will be the base for the quiz tonight. So we have first part of the quiz, and at the end of the quiz, obviously there's some rewards for something to win for winning the quiz. So Sila, I think see you ready. Go ahead.
Hello everybody. I hope you joined our online school. And now we will have one presentation for the Professor Walter Ambrosini about nuclear energy. And after that, Professor David Legradi about medical imaging will have the presentation. After that, we will have a small break and some laboratory work you can see on the screen. And after that, the quiz session made by Mattia.
Okay. And so we first have the presentation on nuclear energy by Walter Ambrosini, and Sila, as far as I remember, so we'll have questions afterwards, huh? So
yes, I hope, because Walter is with us, we will see his presentation from the video, and after that, if anyone has any question, I hope that Walter can answer on it.
Answer the questions, exactly. So then I asked Mattia to launch the video, unless there are questions from the audience. Anybody questions there?
Tutti a cenno col dito pollice che vi facevo capire che era andato bene.
Walter, my Italian is not so good. Was this for us? No, it wasn't. Okay, Mattia, please go ahead and share the video.
Yeah.
Good morning. My name is Walter Ambrosini. I'm professor in nuclear plants at the University of Pisa, Italy. And I was assigned by the organization of this nice summer school the job to produce a little document, let me say a little presentation on nuclear energy for the present and the future. So this is something I am doing very eagerly. This presentation, as I say in this slide, is conceived for secondary school students and has the objective of a general introduction to nuclear energy as a means for producing electricity, something which is very much important, as I will say now, especially in this period in which we have to convert very much all our energy production maybe into electricity in order to be cleaner. The slides contain multiple links to Wikipedia and other resources, web resources. So once you will have it in a PDF format, which I ask the organizer to distribute it to you, you will have the possibility to deepen some of the concepts I will go through in order to understand a little bit better the concepts which are behind. The presentation is by no means exhaustive. This is something I have to say. I will finish it with a sort of touch of art. Remember, something about art and poetry, which are related anyway to the subject I'm discussing. Wine producing energy. In the past century, the one that finished with the year 2000, we have witnessed a very big technological progress offered to mankind, unprecedented opportunities. We had more efficient communications, more powerful and intense sources of energy from wood to oil and carbon, and then to nuclear energy as well. And better quality of life in general, food, medical care, welfare in general, I would say, because we have to distinguish the fact that there are regions of the world which were not very much involved in this development. It can be anticipated that this development process will be subject to a continuous expansion. We will have more and more sophisticated technologies. The ones that you see here can be looked at as a little bit out of dated, let me say, with respect to what we have today. But there is also a part of the world population which is excluded from the technological and social development, and they are claiming their right to share the achieved benefits, and we cannot deny that. Why we have to produce clean energy, and this is a subject which is discussed in this decade, the one which started from 2020 and will end with 2030, because it will be a key one for this thing, because we are in front of global warming and climate changes, for instance. It is, let's say, these are two of the concerns. And the issue of reducing carbon emissions in the atmosphere is devoted greater and greater attention. There have been high-level statements which are stressing these needs for a stewardship of nature and the environment we live in, which is our home, our common home, let me say. These worries have been expressed by many. For instance, you can have these links, a document of the, let's say, a link to the page of the Intergovernmental Panel for Climate Change, and you will see that they are producing periodically some reports. There are speeches of relevant persons. For this year, I selected a page which is reporting about Bill Gates, who published an interesting book and very accessible to everybody, speaking about the cost of the ecological transition. And even in the well-known Francis Pope document, which is called the Laudato Si, at which there is a link, everything is telling to us that we have to do something in order to produce cleaner and cleaner energy. There was an important communication by the European Commission, which is called a Clean Planet for All, which came at the end of 2018. It was in November 28, 2018, which was sketching different scenarios for the production of energy in Europe in the future. There is a sentence which is very much important, which says that by 2050, more than 80% of electricity will be coming from renewable energy sources, increasingly located offshore, which means, let's say, in the sea, together with a nuclear power share of about 15%. This, let's say, this quantity, actually, this number has been a little bit criticized by, because it seems too low. But anyway, this will be the backbone of a carbon-free European power system. So nuclear energy is considered in the backbone of the carbon-free European power system. There is another document which has appeared recently, and it is very interesting to read because there is a comparison between the different sources of production of electricity and in general of energy, which is let's say, which was asked by the European Commission to the Joint Research Center, which is the scientific arm of the European Commission. This report is stating that the analysis did not reveal any science-based evidence that nuclear energy does more harm to human health or the environment than other electricity production technology already included in the taxonomy, which is just the set of norms and regulations in order to get access to fundings for design and so on. as activities supporting climate change mitigation. So it was recognized that nuclear is not more dangerous than other. Carbon dioxide is one of the gases we believe to be responsible to alter greenhouse effect, which is, let's say, this effect for which the atmosphere is retaining part of the radiation which is incoming by the sun. The presence of CO2 and even more methane in the atmosphere, but also other components like nitrogen oxides, for instance, causes a greater fraction of solar radiation to be retained. Low CO2 emission energy are being considered necessary in order not to alter this equilibrium that was established in very long periods during the life of our Earth. Nuclear energy is sometimes excluded from the future energy mix by someone who think that nuclear energy is dangerous or whatever. But you have seen that there are also some positions at the European level and in general in the world which are supporting nuclear energy. In particular, in this page you can find some links that I suggest you to follow, in which you will see that there are different initiatives. One is called Nuclear for Climate, which means nuclear in favor of climate, which stress this point. And there are 3 videos that you can look at that. I just mentioned also James Lovelock, who is a scientist, a well-known scientist, which was the one who proposed the Gaia theory, which is a theory of the Earth seen as a sort of big animal, if you want, in a holistic perspective, as we say, in a whole perspective, which is reacting to the disturbances that human race may bring to it owing to its action. James Lovelock, who is a scientist more than 100 years old at the moment, actually is strongly in favor of nuclear energy, notwithstanding this environmental perspective, global environmental perspective he has suggested. However, we have to admit that not everybody agrees on nuclear energy to be part of the solution. So it's better to go deeper. And this is why I'm showing to you something about that. Here you can see, for instance, some of the milestones that brought to the exploitation of nuclear energy. One was the discovery of radioactivity by Henri Becquerel, and it was in 1896. Then Pierre and Marie Curie, who isolated radium, the special relativity by Einstein, which put the basis for understanding something which was important, but also the atomic model by Rutherford and the one by Bohr, the development of quantum mechanics by Schrödinger and others, the discovery of the neutron by Chadwick, which was an important milestone, because you will see that neutrons are having an important role in our story. Then the discovery of artificial radioactivity by the Joliot-Curie couple, and then Fermi and his Panisperna boys who played with fission before the discovery of fission. The discovery of fission itself by 2 Germans, Hahn and Strassmann, and the explanation by Elise Meitner, who was a very skilled scientist who in the Christmas time of 1938 provide the explanation to what Hahn and Strassmann has, let's say, discovered. And she said that in a very colored way, saying fission is a sort of an extensive burst. But let's see what is fission. Radioactivity, first of all, let me say, is the emission by some unstable nuclei of radiations which are have different penetration capabilities. Alpha radiation, which can be stopped by a paper sheet, beta radiation, which can be stopped by a few millimeters of aluminium, and gamma rays, which can be stopped only by sufficiently thick layers of lead. All this is a form of nuclear energy, which is produced spontaneously or artificially from some nuclides which have been which are present naturally in let's say on the Earth, or have been generated artificially. And I wanted to say just this one. Natural or artificial radioactivity is a form of energy released by the matter. Anyway, Rutherford was somehow skeptic at the beginning about the possibility of using this quantity of energy produced by radioactivity, because it is really tiny, let's say, on our scales of energy production. But then there was the discovery, as I told you, of fission. What is fission? Fission is a nuclear reaction, and it involves the nuclei of atoms, especially the nuclei of heavy atoms like uranium, for instance. In a fission, a heavy nucleus, which is uranium in this case, is split into lighter nuclei, as you see in this process, emitting energy, and also two or two neutrons. The point is that one neutron is triggering this process, and neutrons are produced. Since the mass of the reaction product is lower than the one of the initial nucleus plus the incoming neutron, there is production of energy, which means that there is the equivalence, and this is due to Einstein, as you know, between a defect of mass and energy, as you see here. And this is one of the best known formulation of the last century. And so the defect of mass is in the product of the nuclear reaction is converted into energy. Fission produces different lighter nuclei, which are called the fission products. They possess 80% of the energy produced in form of kinetic energy, but they are slowed down into the material in which the fission is produced. And while being slowed down, they excite the movement of all the other atoms, and so they produce heat. Fission products are mostly radioactive, and then they also emit energy while decaying, and it is one of the problems, let me say, related to the safety of nuclear reactors based on fission. Anyway, the concept in this slide is that fission can be therefore used to produce heat, and that's why we can use it in place of, let me say, a burner, like in fossil fuels, let me say, in fossil fueled plants. Since fission produces also neutrons, it is possible to think to something like you see here, which is a chain reaction. The idea to get a chain reaction, which means one nucleus, one neutron is, let's say, split into nucleus, two or three neutrons are produced, and they're available for further fissioning of other nuclei, and so on in an, let's say, expanding process, is called the chain reaction. And it is an idea that has been attributed to a prominent Hungarian scientist whose name was Leo Szilard, and who had this idea. In a nuclear reactor, actually, we have what it is called the four factors formula, which tends to give us the perception of how a generation of neutrons is propagated, and let me say, to the next generation in terms of the processes which are due. Here it is a sketchy way of showing this. There is, let me say, and the neutrons are produced, let me say, in the past generation, and we would like to see at the end of this circle that you see highlighted by the arrows to have the same number of neutrons in the end. And so you will say that the reactor is critical, which means the reactor is self-sustaining. This means that all these processes, which is fast fission, neutron resonance escape probability, neutrons absorbed in the fuel, neutrons produced by thermal fission, and neutrons which do not leak from the reactor, should make, let me say, the same number of neutrons that we have at the beginning, which means that this product, epsilon p f eta by pl, should be equal to 1. This is something which is called the multiplication factor, the effective K, as we call it in jargon, of, let's say, neutron transport, let me say. So K effectives is just the ratio of the neutrons in two different generations. If it is greater than 1, the number of neutrons increases, so we have a supercritical reactor in which power is increasing because the number of neutrons is related to the possibility to have fission, and so to the power which is generated. If it is equal to 1, as Enrico Fermi was able to do in his first experiment in CP1 in Chicago Pile 1, then the number of neutrons is constant in time, and we have a critical reactor. Otherwise, if the K effective is less than 1, the number of neutrons decreases, and so we have a subcritical reactor. Nuclear reactor during steady condition, it must be K effective equal to 1, and it is what we want to do. This is just a sketchy way to show how in time the nuclear reactors can behave when they are supercritical, critical, or subcritical. So you see that we would like to have a stable production of energy in the reactor, and this means that we should follow this magenta line that you see here with a K effective, which is equal to 1. So how do we do that? Generally, we try to have breaks in the reactor itself, and these breaks are called control rods, because the control rods are made of some material which is absorbed in the neutrons. So if there are neutrons in excess, we want to decrease let me say, the quantity of this neutron, and so we generate greater absorption by introducing the control rod in the reactor. Otherwise, if we need to go up in power for any reason, we will extract the control rods and we will have a lower absorption. This is a very simple concept, if you want, which is anyway complex enough when you need to implement it in a real reactor. The number of neutrons and then of the produced fissions determines the produced reactor power. Even after the termination of the chain reaction, the core produces what it is called the decay heat coming from fission product that should be removed to avoid heat up of the reactor. This means that even if we have the scram of the reactor, which means scram is a jargon word which just means all the control rods must be in, the reactor cores need to be cooled because there is no more production from the fission, but there is production by the decay of the fission products. The reactor contains generally a lot of different materials. For instance, the fissile material, the one which are able to undergo fission with whatever neutron energies, and uranium-235, plutonium-239, and uranium-233 are the isotopes which can be used. Consider that only uranium-235 is actually in natural uranium, and the other are created artificially by bombarding some nuclei with neutrons. Then control materials for the control rods like boron, silver, indium, and cadmium alloys, which are used for the control rods. Moderators for slowing down the neutrons, and they are using light water or heavy water, which contains deuterium or graphite. And fertile materials to have the conversion to plutonium or uranium-233 when it is not needed, and structural material. How the nuclear reactor core, which is the part in which power is produced, is made. It is something similar to what you can say with elongated, in general, this is one of the types, let's say elongated fuel elements of parallelepipedal form, which are put together just to form something which is seemingly cylindrical, let me say. So the mass included in the reactor core is totaling some 100, 150 tons. It depends on the size of the reactor and whatever. And it is generally sufficient for a 1000 megawatt electric reactor for 3-4 years of operation. So you see that just this little amount of material is producing so much energy for 3-4 years of, let's say, a very big reactor with 1 gigawatt, we say, of megawatt electrics. The core of a common reactor type is very similar to a cylinder, as you see, being more or less 4 meters in height and 3 to 6 meters in diameter. That's all. This means that in order to produce the energy, we need very little material. So when you hear about the nuclear waste and so on, okay, nuclear waste are dangerous because they are radioactive, but they are a very tiny fraction of the waste which are produced by mankind during the, let's say, their life, which means, for instance, that in a country like France, in which 70% of electricity is produced by nuclear, they account for only 0.3% of the total waste which are produced by industry. So also the volume of fuel and waste is small, and this means that we have a very intensive energy source with little material. Protection from radiation. Radiation is in our environment. We have some radionuclides in the Earth crust, like potassium, rubidium, thorium, uranium-238, who are spontaneously radioactive. Our body contains radioactive material, so we are normally exposed to radioactivity, and this does not generate specific pathologies, let me say, unless we can trace back some particular behavior, which, and you can also see that the total in these units, which are millisieverts per year, the total natural sources account for the greatest share of the total of the exposure to radiation that we have, which is by, let's say, 3 from this textbook. This is the table which has been taken. Then there is also some contribution from medical sources, not only natural sources, but medical sources. And the nuclear fuel cycle is producing just a tiny amount of increment. So that's why we can say that nuclear energy is safe enough in that situation. Some principles are being applied, and invite you to deepen a little bit the thing. I have no time to really spend too much on these, but there are some international bodies like ICRP, the International Commission for Radiological Protection, who set out some principles by which you can use radioactivity in your activities. These principles are, in a nutshell, very small, very simple. Justification, you have to justify actually if you want to use radiation more than the one which is coming to us, as you have seen, from the natural exposure. Optimization, which means that if you want to use radiation for specific purposes, for instance, a medical application or the construction of a nuclear reactor and operation of it, you have to optimize, which means you have to reduce at the lowest possible limit with the so-called LARA principle, which means as low as reasonably achievable, the exposure of people. Then you have to respect some maximum admissible doses which have been established for the different groups of population, from the workers exposed to radiation, like my daughter, who is a radiologist, and others which are in the common population. Defense in depth concept. This is one of the concepts which have been introduced since the very beginning in order to design in a safe way the reactors, because we have to contain radioactivity which is generated in the nuclear reactor when it is working. There are 5 levels of this. You can see 3 of them, which are put into evidence here, are introduced in order to avoid 2 severe accidents, and then the 4th and 5th are there in order to manage the possible occurrence of severe accident. So you see that logically we have to design the reactor with maximum quality of and safety of the components. Nevertheless, we have to assume that accident will occur anyway and provide engineered safety features which are introduced in order to let's say, back up the possible malfunction. It is a perfect machine, but it may anyway, let's say, anyway fail. So we must be prepared for that. Provide additional measures in front of some specific accident scenarios that we underline as design basis accidents to be used for the analysis of the safety of the plant. And then another concept by which we design the reactors is the so-called multiple barrier, which means that the escape of radioactivity must be prevented by physical barriers, which are the fuel. You see, a pellet like this, which is small like my little finger, the last part of my little finger, is the basic part of the fuel, which is made of uranium dioxide in most of the designs. Then the cladding, which is a tube, which is of zirconium generally, which is encasing this material. And then this is put in a sort of core, like the one we have seen before. And around it, there is the reactor coolant pressure boundary. And then we are not satisfied by that because we put over it also the containment building, which means that we have 4 barriers that must be broken if in order to have the release of radioactive material to the outside. Nuclear fusion. We have spoken up to now of fission, but there are also different ways in which fusion energy is harvested. And fusion, what is fusion? Actually, it is a different different nuclear reaction. Here you can see some links to the ITER machine and let's say the design, which is a project which is going on in the southern part of France, close to Aix-en-Provence in Cadarache. And so here you have some material to deepen a little bit the knowledge of that. There is a big machine which is being built. While fission now is a reality in commercial field, fusion is not yet. But it is another important, let's say, way in which we hope. Let me say, there are different processes by which nuclear, I just touched while finishing my lecture, one of the most debated issues. There are many. There are some related to accidents, related to the level of safety. I try to say something about that. But let me say, one which is often very much considered as worrying is the one of nuclear waste. This one of nuclear waste is actually considered as a major problem, unsolved problem of fission, which is not the case because there are places for instance, in Finland, but also in the United States and in many other countries in which the wastes are presently conditioned. But we are just at the beginning because the use of nuclear energy is dated back just a few decades. So we have just limited experience on that. What we do with the waste, you see here in this picture, there are deposits, which are repositories, they're called, which are just tunnels which are dug into the ground to some hundreds meter below the earth crust, or within that earth crust, if you want, where, let's say, we can put this little quantity of material which are dangerous, the ones which is produced in the reactor core. So you have seen that it is a small fraction. This is what I insist to say with respect all the waste that we are generating in our life, let me say. And this little quantity can be disposed of in a safe way in these tunnels. Here you see something where you can, let's say, a little, how to say, sketch of many things you can look on the websites and see about the reprocessing, the partitioning and transmutation of the fuel, which are some of the newest ingredients, let me say, in this frame of the barring in stable geological repositories, like salt and granite formation, geological formation, which are particularly apt for keeping the nuclear waste. So the message is we have technologies for deal with the little amount of nuclear waste which is produced with the nuclear energy. Opportunities of study. Now I'm speaking to students. I have to tell you that there are Master of Science in different parts of Europe and worldwide in which you can learn about how to become a nuclear engineer, or also a nuclear physician, for instance, or let's say to have a role in the exploitation of the youngest of the energy sources we have been gifted by life. The European Nuclear Education Network, which is in whose frame we have this summer school, is an organization, an association that in Europe collects more than 70 member and associate member institution, universities, but also industries, research centers, and so on, which are actually making an effort to keep and make more and more effective the education, the higher education, university level, in the nuclear field. And you see that now we are speaking also to secondary school students in order to enlarge a little bit our panorama. If you click on this logo, you will have the possibility to visit the website of the European Nuclear Education Network. And there you can find a lot of resources and some description of the activity of the activities of the association. I'm coming to the end of my speech, and I hope that then you can somehow, let me say, deepen the aspects that I have touched very briefly in the 30 minutes I was granted in it. I will finish, I generally finish with a touch of Earth. We started, let me see if the link is working properly in this condition. Not sure. Okay, yes. I have linked to a page, let's say found at random, which is, let's say, referring to one of the very interesting and very well-known image by Francisco Goya, which is which in Spanish is called el sueño de la razón produce monstruos. Sorry for my very bad Spanish, which means while the reason is at sleep, you have a monster which are created. And this is because, just to say that nuclear is now feared very much by population. There is an aversion against nuclear energy, which is very widespread, unfortunately, as it was, I must say, for vaccination just before the pandemic. Now, almost everybody is convinced that we need a vaccination. Before, there were so many people that were saying, no, no, vaccine may be dangerous. So, yes, they have some possible, let me say, byproducts if you are sick, if you are not apt to be vaccinated, and so on. So you must pay attention, but it is much better than having COVID. This is the idea. So now the same can be said about nuclear. We can be afraid of this very large amount of energy that we are granted by using nuclear energy, but really we have not to abandon our reason. If we use it in a proper way, it will be a strong advantage. And this is the touch of art. Then there is a touch of poetry, if I am able to reach the link very quickly. Okay, this is the other link that you can see. It is okay. And here you find what it is called the Ode to Atom of Pablo Neruda, who is this guy you can find here, and which was written in 1954, just after the Second World War, a little bit, 9 years after. The Ode to Atom, I suggest you to read it with your teachers, for instance, and comment, is saying a concept which is very much important. You know that nuclear energy has many, let's say, inventions, or discoveries, as we can say, were used also for military applications. The first use was a military application, the bombing of Hiroshima and Nagasaki. So the poet was just saying, okay, you entered nuclear energy, you entered the atom, let me say so, nuclear energy. You entered the scene of mankind in a brutal way, which is just, let's say, for military purpose, but you have the power to do a lot of benefit. So let's try to get the best we can from nuclear energy for peaceful applications, and it is actually the sector in which we more let's say a lot of people is working, like me, or let's say our colleagues, the ones who organize this meeting. So this is a summer school. So actually, I thank you for your attention. And if you need to contact me, you can find me easily on the web, and please send me an email. I just regret I didn't say at the beginning of the fact that I couldn't be with you as planned because of, let me say, a conflicting engagement, which is a very, let me say, engaging one. So I couldn't be there. And so I decided to record this video clip. So thank you very much. And please have a look to the presentation and try to deepen with your teachers some of the aspects. If you need any support or you want to put some questions to me, you will know how to reach me very easily by Googling my name in Google. Okay? See you. Bye.
Okay, thank you very much. Okay, thank you very much, Walter. We're running a bit late, but still, I mean, I see that Walter is here. Walter, are you here? Can you make a sign?
Yes, I am here.
You're here.
Please.
Okay, so great. So if there are questions, I still say, even if we're running late, we would take these questions. So are there any questions? Possibility to ask a nuclear expert everything you ever wanted to know about nuclear? Okay, maybe I can ask a question because Chernobyl was mentioned so many times. Walter, can you give me three main principles, differences between the way the Chernobyl reactor was constructed and the modern reactor is constructed?
Yes, of course. Let me say there are different points by which the Chernobyl reactor RBMK 1000 was different from Western reactors. So it was designed actually not to be completely stable, and this would be something avoided by General Design Criterion number 12 from the Appendix A of 10 CFR 50. You have to design something which is always stable, let me say, or you can detect and suppress the instabilities. This was one of the things. The other thing is maybe training of the people, which were not very much in a noisy environment, which were not that much trained to cope with this kind of possible occurrences, as we saw also in movies. The lack of nuclear violation, let me say, of many safety requirements during the operation of that night, in which, for instance, the control rods that we saw were mostly extracted from the reactor, and this is really forbidden. So it was something that actually demonstrated what I said before, which is like the lack of safety culture in the training of the operators. We don't want to blame them too much because it was a very let me say, particular situation in which they were compelled to do an experiment that they should have stopped. You know, I can just, let's say, mention something. I had to undergo a little surgery that I did today, but 15 days ago, the anesthesiologist actually said not possible. At the last moment, I was already in the operating room. This is safety culture, you know. I was upset about that, but this is safety culture. So if they had stopped like that in Chernobyl, we would not be speaking about Chernobyl. This is the point.
Okay, thank you very much. No other questions? Okay, thank you. So then I hand over to David Legradi. Are you with us?
I am. Do you hear me?
Yes, we can hear you very well. I
Okay.
can't see you yet. Maybe I'm on the different screen. Let me see. Maybe Matija, you can highlight David so we can see him. David, I understand you will be sharing your presentation yourself, will you?
Yes.
Okay. And with regards to timing, we just continue like this, so we run a bit late today. I apologize, but it's like this. Okay.
I'll try to save back a bit of time. We'll see how I manage. Oops. Just a second. Okay, can you see my presentation?
Yes, perfect. Thank you.
Okay, then I'll start it. My idea is to go slow, show only a little, in the hope that you will understand everything. If I do not succeed, just stop me, ask a question, indicate me that I should go back. You can also rush me to say, okay, that's too easy what you are trying to explain. What I'm trying to tell you about now is about imaging, medical imaging, starting with how a simple image is born, and afterwards how to translate that to producing a medical image. And if you manage to produce a medical image, you can also do tomography. Whoever does not know what tomography is, I hope after the end of this presentation, will know it exactly what tomography is and what is the difference between taking loads of images of the same object and tomography. I also would like to talk about the machines that will produce those images, and I also hope that whoever is already familiar with these equipment will have new knowledge about them or a new way of understanding them. So let's start with how to produce an image. What would you need? Normally you would have a photo camera. That means in your telephone you have a photo camera. Now I will dismantle your telephone, and instead of that I will show how a big photo camera works. It's the same principle. So what you would need, first of all, is a position-dependent pixel sensor. What do I mean? I mean that you see a CMOS sensor now as an illustration. You have loads of small pixels in it, typically 1000 times 2000, something like that. And every single pixel records the light independently. That means that the light that hits one sensor will not be recorded by the neighboring sensor, but only that sensor. And normally you would need a lens. And now that would be my question. And normally if I give such a lecture for a live audience, then I can ask this question, why would you need a lens? And I'm sure you will have some answers. Well, it focuses light. It will give more light to the sensor. But to highlight, there is a very important feature to this lens in terms of image forming. I took my own camera. Normally, if you are with me in the same room, I would show my camera, but now you have to believe that I do have a camera and I can dismantle it. And what I did, I just took my camera and took off the lens and took a photo. And this is the photo that I've taken. You see a white screen, perhaps, depending on your resolution and also how that transfers to the internet. But it's not a fully white screen. It's not a so-called white screen of death. It is an image that I've taken with my camera. How would you be able to see that? Well, maybe you see small dots on it, but maybe not. You have to now believe me that without the lens, that is the image that you get. And why is that? Before I tell you that, then I took another experiment. I took the same camera, still without a lens, and I covered my camera with a piece of paper. And on a piece of paper, I made a very tiny, small puncture, a small hole. So now it became just a paper with a small hole. And I took another image. Maybe you have an idea of what you would see in the next slide. You have already seen because I made a mistake, but you may have the guess that you will see only the picture of that hole. But what in reality you get this one. What you see is a plush toy of my daughter, and I just put it in front of my camera. You also see the small black speckles that is on the sensor of my camera. And what happens, you get an image on the sensor. When there was no paper in front of the camera, you did not get. When you have a paper with a small hole, you do get this image. Now I replace this paper with a lens. So I put on the lens how normally you would use a camera, and I produce another image. You see it's a lot better quality, but you still see the same object in front. So if I would want to put those together, you need an object that has contrast in it, so it has different white and black parts, because otherwise you would see a totally white screen. But even if you have such an object, you would need some equipment that is like a lens, or it's like a piece of paper with a hole in the middle that will translate this information somehow on your sensor, that it will be recognized by a visual observer like us. But what is this information that somehow gets taken out when you put a piece of paper in front of a lens? And it will produce almost the same results when you put a lens in front of a camera, not a piece of paper. So first we have to understand, if you do not put a paper, do not put a lens in front of that camera sensor, why would you not get an image? And the idea is that on the right-hand side, you have the skeleton. On the left-hand side, on the imaging sensor, you will get light from the head of the skeleton to one part of the sensor, and from another part of the skeleton to somewhere else. But the light goes in every direction. So if you just take a look at the pixel, so if you see my cursor, for example here, light will come from this part of the skeleton, but it will also come from other parts of the skeleton, all gathering in the same pixels. So what the problem is, if you have a space-dependent sensor, in every pixel, you get all the information of your image. But the problem is that information is all mixed up into one big pile. And from that point on, you cannot say what your image was originally, because every pixel sees every information, and that is bad. And that is why you can't get a nice image. What happens if you put a piece of paper in front of, this is the sensor now, this is the object, this is the piece of paper with a hole in the middle. What happens then? Now light, again, tries to go from, for example, this direction, and it will get blocked by the paper. Another streak of light goes through now the hole. Okay, it reaches the sensor. Excellent. Now, again, a new line goes through the middle of this hole and then reaches the other part of the sensor. But the main idea is that you, if you take one part of the sensor, you can only get light there if it came through the hole. And there will be only a single line that can produce an image. And that means at the end of that line, there will be only a single part of your object that is visible by a single pixel. That means now the information is selected for each pixel separately. Each pixel sees only one part of your object. And even a single piece of paper can do that. If you just connect the lines, you will see we'll get an upside down picture. Now, I'm sure you have seen small circles in the shade of trees. You see the small circles here. And my statement is that these small circles are not an image of the small holes in the leaves. It could be possible that worms have created a small, exactly circular hole in the leaf, and that's what we are seeing here. My statement is that what you see here is the light coming through very small holes in the leaves of the trees, And those are the images of the sun. This is an image of the sun, and that is the image of the sun. And that's why it's perfectly circular, because we see the image of the sun as a circle. Now, it's a nice statement. How could you prove it? What would be the easiest way to prove or disprove my statement? Well, you just have to wait a bit. I show another image. Again, you see some circles. They are perfect circles here and there and there. Some circles are mixed together. So how would you be able to prove or disprove my theorem that these circles are actually images of the sun? Well, if you wait for the solar eclipse, when the moon goes in front of the sun and starts blocking out some light coming from the sun, that means you will see a small crescent of the sun with proper sunglasses. But if my theorem is right about the images of the sun, on the ground, you will have to be able to, instead of circles, you have to be able to see small crescents. And that's what you see. So if you take a look at all these shadows when the moon is covering the sun, now partially, that instead of the circles, you will get those crescents. So my statement seems to be okay. Okay, that is one way of making an image, but if you you have a lens, it can do the same in a better quality. But why does it work the same way as a simple piece of paper with a hole inside? Well, if you learned some optics, then one way to show it is to take a look at those streaks of light that are parallel when reaching the lens. If you learned optics, you will see that all these lights will go through the focal point of the lens. So if a piece of light comes from the head of my skeleton, it will bend at the lens and it will go through the focal point. At the end, it will reach one part of the sensor. This focal point is an artificial thing. It's not an object you can touch, but you can calculate where it is. If you take another streak of light, reaching the lens, it will again go through the focal point. And thus, the lens will also separate the information that each point of the sensor will only see one part of the object. So the principle is very similar. And if you start thinking about it more, you may come up with other ideas how to make the same thing. To give it a name, I will call those lines that will connect only a single point of the sensor with only a single point of reality of the object, lines of response. These lines of response is essential for forming an image. You could do it with different techniques, but for many of the medical applications, you could work with this concept. If you can make an equipment that forces the information coming from the object to lines of responses, meaning that only a single point of the object will be reflected on a single point of the sensor, then you have the hope of creating an image. Now, I would like to go for the principles of medical imaging, so to show how that principles are used in medical imaging. You cannot use a lens because the light that we are using for medical imaging is not visible to the eye. If it were, it will not pass through the body. This statement is not 100% true. I wonder whether you have tried to put your hands in front of a normal lamp, like on your desk. You will see no light will come through, apart from a bit of red light, because human flesh is transparent to infrared radiation. So some part of the red radiation can come through your body, but it will scatter a lot, and you will not be able to force this line of response concept to visible light. So basically, visible light is ruled out, and optics, meaning lens, is ruled out for deeper tissue medical imaging. So if we are talking about non-visible light, it's very hard to build lenses for that. Actually, it's almost impossible. Some with some approximations, X-rays can do some lens effects, but let's say it's mainly not possible. So lenses are ruled out. We need some new idea, and one would be to playing a pirate game. I hope you have done that in your childhood. You take a toilet roll middle, or you just take a long tube and you look through it, and you will only see one part of reality. It is not a magnifying glass, but you can play it with it like a magnifying glass. If you look through it, you will only see one part of reality. You could build the same for medical imaging. Now imagine loads of tubes next to each other. And now it is the cross section of it. So that is one part of the tube, other part of the tube. And in the middle, there is the hole. And again, here's the hole. And let's build this out of lead instead of paper. So it will not let through X-ray or gamma radiation through the green walls, but it will only let the radiation through the gaps between those walls. Again, it will force reality to only deliver information using X-rays or gamma rays from the object, a single point to a single point on the sensor. This we will call a collimator, because now the lines of light are parallel. You can also in Latin call it like collinear. So this will collimate, this will align the directions of light according to parallel fashion. So this collimator made out of lead is used very often. But that is not the only other principle that works like a line of response concept. I can show you another one that, okay, this one is used for one type of imaging. Let me better explain it first. What is used for reality, you have a patient, and in the patient, you have radioactive tracer drugs. That means some chemical compound, an isotope that behaves exactly the same way as other chemical elements, except for emitting radiation. These gamma photons that are emitted by the patient, if let through by these walls, these lead walls, on the other side, if you have a sensor that is position dependent, will let you make an image of the distribution of the radioactive isotope inside the body. So then you can see where the radioactive isotope accumulated, and with that you can make a diagnosis. Who discovered that? He got a Nobel Prize for this guy. He was a Hungarian, George von Hevesi, and he got nominated something like 14 times, and he didn't get it, and for like 5 different reasons. So if I can give you a piece of advice, if you want to get a Nobel Prize, come up with loads of ideas that can win a Nobel Prize, because after a while you may get it. If you have a single one, it's like buying a single ticket of lottery. It's a lot more chance to win a Nobel Prize if you have more Nobel Prize ideas. So take my advice. He got nominated for X-ray spectroscopy, and but now what is important for us is the discovery of the tracer principle. And the idea was that he could not separate radium-D from the element lead. And after half a year of trying, he said, okay, if I can do it, then it cannot be done. It must be the same chemical element that is working in a physics way different than the other same element. And with that, you can label something that is chemically sensitive to lead, for example, and then you can label with a radioactive isotope that compound that goes through the body, and then you can monitor where that compound would normally go. Okay, I will show you another idea how to make this line of response concept working. And I also think that you have done that before. If we have a light source in that side, light is going in every direction, as we have discussed so far. If we have this position-dependent sensor on the other side as well. And if you put an object in between those lines, as you may have done with projecting the shadow of your hands on the wall, you will get a magnified image, at least the outlines of it. And that will be called projection imaging. And again, you see only one part of the sensor, only one point of the sensor is connected with one point of the object, because it also has to light on the light source. So that will enforce the light to be on the same line of response. Okay, you can do this magnification mathematics that I usually show to show you that with secondary school mathematics, you can not only get the magnification of the object, but you can also get a magnification of the source. If your source is not a point, you will get an object that is not very contrasted, because at the edge of your hands, you will see some shadows. But now, lack of time, I will skip through all these equations, but they are quite simple. And the outcome would be that if you put a patient very close to the source of light, you will get a magnified image, but you will get a bad contrast. If you put it very close to the sensor, you will get a very nice contrast, but low magnification. But now I will skip through to more interesting things, perhaps. I should have been faster before to show this as well. I want to show what the equipment are. And this one is not an equipment on the left-hand side. On the right-hand side, it is. It's an X-ray source, and it was discovered by Wilhelm Conrad Röntgen. And he was the first Nobel Prize winner in physics. And immediately that was awarded for medical imaging. I already talked about how to win a Nobel Prize. That was the good news. The bad news is that they have already won loads of Nobel Prizes in medical imaging. So if you want to do medical imaging and winning a Nobel Prize, well, you have to speed up. It's not going to be easy. I tried. Okay, so you have Röntgen. He discovered the X-ray radiation and immediately made an image of his wife's hand. And you can see on the left-hand side, very famous image. In every radiation-related thing, they show it. So that is the hand image X-ray with X-rays of Wilhelm Conrad Röntgen's wife. That was called Anna Bertha Ludwig. It is not often said. Now she looked at the image and said, never again, because she believed that she sees her soul. Actually, she sees her ghost. So she didn't want to take any more images. Now there was this guy, Edison, who thought, that's fun, this imaging thing. And he took it to village fairs to say, I can make an image of your soul. After a while, they discovered, the engineers operating these machines, that they started losing hair and stuff. And after a while, they realized it's not only a positive effect radiation has on a human health, but also negative. That is the present day quality of an X-ray image. You can see the difference. Same hand. I think the hand did not change much in quality in the past years, but you see how the quality of radiation, of X-ray imaging evolved in the past 100 years. What I also want to talk about is tomography. That is from Greek saying writing slices. And the idea is that if you have an object of a circle and you make an image of it to an imaging plane, it will get exactly the same image if you had another circle further away from the source. If, however, and you can't decide which one was your original image, so small circle, big circle. But if you rotate this image, saying that if you rotate your source and detector around the image, or the image is rotated, and you take images from every point of view, then you can reconstruct. You can now see almost in the middle a circle to say, yeah, well, it was a middle-sized circle in the middle of the objective plane. The mathematics is somewhat more difficult than that, but the idea is this one. And before you would say that taking loads of images from every point of view is the same as tomography, I will try to show you an image. And I would like to ask everyone to try to decide which direction this head of the parrot revolves. Is it, if you would imagine an axis going now from the floor to the ceiling, around that axis, is it going clockwise or counterclockwise? Now, in a normal room, if I ask this, I would get 50% of the answers. With a bit of a practice, you can learn how to change the rotation direction of this video to the other side, because it's just the human brain trying to come up with an interpretation of this image, whether the beak of the parrot is in front. I heard that recording is stopped. I don't know whether you want to restart. I'll wait a couple of seconds.
Sorry, David, just continue. I'm checking out why this happened. I think it's not so important.
Yeah, okay. Because it's not, the information is not in the image, which one is forward, the beak or the other end of the parrot. But if you do tomographic reconstruction with some mathematical tools, you will get this reconstructed image where we know which part comes first, the beak or the edge, the other end of the skull, because radiation just passes through the object without knowing what is in front, what is in the back. Okay, recording is back in progress. So I'm going back to my presentation. Okay, how does a CT look like now? It's like that one. From the outside, they will not be able to see whether this one is a CT machine or an MRI. They are packed almost the same. If you open it up, you will see the revolving source and the detectors around the patient, and the bed is going inside of this hole. So that is how a CT machine looks like, revolving the source and detector and the patient. And this is, okay, I showed you the image of this Lego skeleton. And now this one is a tomographic reconstruction of a Lego skeleton by our own scanner, CT scanner that we have built. You can also see the cross-sectional views of the skeleton. This 3D images now is more for the visuals. That means I could reconstruct which comes first, the middle of the skeleton or the other side, and so on and so on. And that is tomography is capable of. What other techniques do you have for tomography? This one is positron emission tomography. The first idea is that you have a positron born from an isotope. It migrates until it slows down, and after a positron that is an anti-electron meets another electron, it annihilates, it becomes nothing plus energy, and this energy comes free in the form of 2 gamma photons, each having 511 keV, that is the rest mass of electron and positrons combined. If you could detect with the small detector pixels at the same time the post-gamma photons, you can be sure that the positron annihilation happened on the line connecting those small crystals. Again, forcing reality to have one data recorded for a single line of reality. If you make many of these pixels, you see loads of positron emission tomography panels around, and each of these small dots here at the end of each lines are pixels, and they can be connected with every other pixel on every other panel. You will get a positron emission tomography scanner. This one is a simulation done by our software. You can do the same for single photon emission computed tomography, revolving with the parallel collimator around the patient. And as I think I used up all my time, that is what I wanted to show you. I hope you can still see my image. Can you still see my sharing? Okay, I'll stop my sharing. So that was my presentation. If you have any questions, please ask.
Okay, thank you very much, David. So yes, are there any questions?
I see one comment to explain an integral on slide 14. Well, that integral was put there just to make sense of saying that you can simplify that integral to lines of responses. And if you have lines of responses, then you can use very simple mathematics of secondary school mathematics of a magnification of simple triangles. For a longer explanation, we will need actually a lot more time.
Okay, thank you very much. So maybe is there any other question now?
I see another one. Not understanding how I proved that the small balls on the floor are actually the images of the sun. And well, the idea was that if I put a different object in front of my imaging equipment, now that was the leaves of the tree, then I will get a different picture. And when the moon shadows the sun, you will get a different image. It's not the circular sun anymore, but it's the crescent, just one part of the sun. Then on the floor, the shadows became different. Instead of small balls, you got small crescents. You can look it up on Wikipedia. Those images were actually done from Wikipedia. And the terms that you need to look for, and I'm almost sure that you have heard about it, is camera obscura. I'm typing that, or the obscure camera. If you type that in, you will get maybe a longer explanation, and you will see the same images on Wikipedia.
Okay, thank you very much. Thank you. Yeah, thank you for the question as well. Is there another question? One new message. Let me see. Oops.
I still have it. A question. Could it be explained as refraction? I don't think so. Very simple. I don't think so. To make a hole like, if it's a very tiny hole, you will get diffraction, and from that point on, the light will be diffused more. So I think if it were diffraction, you will not get such a nice image of nice contrast image. That is my counter argument, but I accept another counter argument.
Okay, thank you. Another question. Good. So, yeah, thank you again for this very interesting presentation. David, you want to say in 2 words what you're going to do after the break? What is your lab going to be about?
Yeah, just in 2 words. It's also a question to me because I didn't manage to record it. I had technical difficulties, so I'm now trying to show it live. And,
okay.
And I'm really hoping that you will be able to get a broadcast because in the cellar, because of radiation protection point of view. So I hope you will get nice reception. And I hope you will also see how I take an image with X-ray. Now that was a technical difficulty. Somehow I didn't manage to fire up the detector now. It did work a week ago, but I hope I will now. So I hope you will get a nice X-ray images about with the CT scanner that we used. If not, I can at least show how we built up the CT scanner. Okay,
thank you very much. So we have a real life lab after the break. Hopefully. So I suggest it's now, according to my time, 16:33, and I suggest we make a break until 4:45, so 16:45. So we meet again at 16:45. Yeah. Basically, we're running 50 minutes late, so we meet for your lab at 16:45.
Okay. Okay.
See you all then.
Bye.
Bye. Okay, I think we can slowly come back. Okay, is a question to Mattia whether there are still people in the waiting room or everybody is here?
No, there's some people that should rejoin, they are coming.
Okay, fine. So let's give them some more time. David, are you getting ready? Let's see, is David here? That's of course important. I cannot see David here. Let me see on the participants list.
No, he should rejoin as well, I think.
Okay, so we still have to wait for David. He's going down to his, what did he say, to his basement, to his cellar, to the lab. Okay, Mattia, while we're waiting for David, maybe you can say some words about the quiz afterwards,
Yeah, sure.
how we will organize this.
So after the laboratory, I'm going to share with all participants a link that you should be able to click and join the quiz for today's session. So what I ask to you is to join just from one device for each team and to rename your avatar with the name of your team. So as we should have, if I'm right, 17 teams, I should see 17 participants to the quiz. And for them who are not in the same place and are in a separate location, I suggest you to choose just one participant and to discuss among you with the chat you prefer here on WhatsApp, Telegram, as you prefer, and to play together even if distant. So I'll share as well the screen of the quiz so all people can see question and answer on the screen. And basically they are all closed answer, only 6 this evening. And you will have 15 seconds for each question to reply. So we count both the speed of your answer and the right answer as well. And in the end, we will see the ranking, the final ranking for today's quiz. So I'll send you the link after this, the next presentation after the laboratory.
Okay, thank you very much. So one link per team. So you have to decide who, if you're not on the same location, you have to decide who is holding the device and who's going to click the right answer. And for those who are in different locations, you will all be able to see the questions through here, through the main screen, because Mattia is going to share it. And then you have to, in the background, just communicate with each other and quickly decide which answer you want to give. So it's the right answer that counts, obviously, and then if we have many right answers, the speed of the answer counts as well. Okay, so question, is David with us now?
Not yet.
Okay. Let me check my email, whether he's having problems maybe joining. No.
Kirsten, I'm going to call him.
You will call him? Okay, thanks, Sheila. Sila, could you reach him? Sila doesn't. Sila, could you talk to David? She doesn't hear me. A real life situation. Okay, I see that Sila couldn't reach David. No answer from David.
Kirsten, maybe we can wait 5 minutes and after that we can run the quiz.
Okay, let's do this. So
Maybe they have some problem with the technical, maybe for Wi-Fi, or I do not know, because I know that it is a underground laboratory.
Okay, yeah,
We
obviously.
will see.
Okay, so let's wait until 16:55, and then if by then David didn't join, we go for the quiz.
Here we are. Kirsten, I think David joined us again.
Oh, okay.
Can you hear me now?
Yes, David, now we can hear you.
Can you hear me now?
Well, yes, we could hear you also the first time. I don't know, can you hear me?
Okay, now I can hear you.
Okay, good.
Good. I'm sorry for the delay. Now I
see something,
okay.
Yes.
Yeah, it was quite hard to get everything running. I'm not sure I will manage to run everything, but I definitely wanted to show you things. Okay, I'm running a bit late. So now we are down in a cellar, very cozy place. And that's where we built our CT scanner. And you will see that here. I'm trying to move my camera in a fashion that will not get CC. And please indicate me immediately if my connection is breaking up, because it's possible we are down in the cellars. So now what we see is an object that is a skeleton. Behind that, you see the detector panel. This detector panel is sensitive in this area. And here you will have an X-ray source. So you have a small hole here, and through that, the X-ray comes out. You see the window, I hope, where the X-ray can come out. In the middle, you see a precision moving tablet. You have two motors, one here that rotates this guy, and the other one that can shift it sideways. In a normal scanner, you will get more the source and the detector revolving around the patient. Of course, that would be really expensive and very hard to build. As you can imagine, if you want to feed high voltage to the X-ray tube, and also you want to get loads of data down from the detector, then it's very hard to put it in a revolving, fast revolving mechanism. So if you want to build your own CT, it's better to rotate the patient. Of course, this CT is not built for a human or living organism. This guy was never alive. We also have some other objects that we usually scan, and some of them were alive, but it's more like just to test the machine. So this belonged once to a dog. What else would you need? You need high voltage for the X-ray operation. You will need some driving mechanisms for the moving tablet motors. Now only one of them is connected. You will have a computer that is designed to operate the X-ray. And now in our setup, we use a remote connection to log into this computer, because of course safety regulations come first. That means that we have to go out of the room when we want to operate the X-ray machine. Now, when I first started working with X-rays, I was sure that because of the low energy, X-rays will not reflect out of the room. And now I'm trying to show you how this underground cellar looks like. So I thought that none of the radiation will be able to come out. But radiation protection dosimeters told me otherwise. And it turned out that they managed to find their way out, scattering all around through the walls. And we had to reinforce this door with, maybe you see one part of it here, that is made out of lead. And that reinforced the door will block the radiation coming from the detector. So now I will go out to the operation room, and I'll try to show, instead of my camera, the X-ray equipment. So just a second, I need to try to connect to remotely to the computer inside. You see there are loads of technical gimmicks that I had to come over. That's why I didn't have time to actually record at the end a working operational CT. Okay, so now I will log into the computer, hopefully inside. And now I'll try to share my screen as well. Okay, so now I hope you see my screen. Do you?
Yes, thank you. Everything fine.
Okay, that's very good. Now I will try to find my remote desktop. Okay, so now we are logged into the computer inside. And I'll try to initialize the detector inside. And now that is the tricky part that didn't work actually this morning. And I do hope that I will get that working now. Just a second. Oh yes, I did manage to get that networking so far. Okay, let's start it again. Okay, we are getting there. Okay. Now it works. Good. Now what you can see is the detector panel of the X-ray machine. You see rectangle, vertical lines that's supposed to not be there, but it is totally normal not to have an even panel. So whenever you start making an X-ray image of anything, then normally you will have an uneven sensor. In your telephone or in your camera, there will be a software that will correct it out for you. That means that you will get an even screen, like what I showed you in the presentation, a totally fully white background. But we have to do that ourselves manually. We don't do that usually in the software that we wrote here that you can see. But you can imagine that before a tomographic reconstruction, you have to do that. Okay. Okay, so now what I will try to do is to switch on the X-ray. Very hard to switch back to my camera with the remote mode. So you have to believe me that there is indeed a safety mechanism of the door that will break the connection to the X-ray whenever I open it. So accidentally, I cannot put on the X-ray when the door is open. So now I put on the X-ray if everything is fine. I have to figure out this problem. It seems that it cannot yet open the X-ray. And then it's good that it cannot start the X-ray itself. I'll take a look at it again. Well, now that's tricky that the detector started working, but the X-ray did not want to initialize itself. That's very embarrassing. No problem. Okay, now I managed to get the X-ray on. Now I will start the image, and now you see the outlines of the skeleton. If I increase the current, you will see that the outlines are clearer, but you can still see the pattern given by the detector. Now I increase it even more. You start losing the pattern given by the detector, and you see now the object. You can also increase the energy, and then now you start seeing details of the object itself. Now you see with a higher energy, I started shooting through the object in the middle, and you see now the details. The lower energy radiation was not enough to penetrate the small plastic object, but now with a bit more heavier energy range, you can see now the details. What I originally planned for you to do, we may still have a bit of time to try to do that, is having the same radiographic image. Now we don't have time for tomography to take 10 minutes to turn it around and so on and so on. But my idea was trying to put some water in a cup and see whether a piece of cube can be seen inside. So now I will get into to the object space. I'll put a small cube in a piece of water. Now for that, maybe it's better to show it in the camera. That means I should stop sharing for a minute. Now, if you could see my hand, can you? This one is a professional gaming dice used in casinos. What is special about it, that the edges are not round, but very sharp, because then it will not affect how a dice is thrown. And I used it as an object to test the CT's resolution. Okay, I will put that in inside. For that, I have to stop the X-rays first. Okay, so now I can get in and put in the objects. Okay, Now, what you see is a bottom of glass, just a coffee cup filled with water. And now,
David, I see a question here.
Yes.
What is that pulse representing in the upper right corner?
Okay, this is the histogram of the image. So you see the one blue peak in the upper right part, and in the left part you see another blue peak, and that is just a number of pixels you have for a certain image shape. So now you see the white part where the radiation does not go through the cup of water. And this white part, you have loads of pixels. That is the peak on the right-hand side. And the left-hand side, those are the black pixels, very simply. So what you see is the idea I actually tried to show you. What you don't see. You still see the same plastic cup. Now I will take off the water, and you can see what you can see afterwards. Now, and hopefully you can see now if the image is not too small, I can't make it really bigger. I'll try to put the energy down. Now you can see it more, that on the bottom of the cup, you have this plastic die that was not visible before. And it was not the cause that the X-ray radiation could not pass through. You asked the histogram on the right-hand side that was not full at the maximum. So there was still space of radiation that could have gone through without saturating the pixels. But what I try to show you is that you have something like now an 80 kilovolt of acceleration voltage on the X-ray tube. And for those photons, a piece of plastic and water seems totally equivalent for the X-ray radiation. So what I try to show is that if you want to see any contrast in a patient, you really have to look for differences in density first, and second on material composition. So now I'm really over on my time. So that's what I wanted to show you now. I'm really sorry for the technical problems. The idea was I would record this beforehand without the technical problems that I kept having, but now I managed to solve those. So that is that. I'm now trying to go back to my Zoom screen. And then if you may have further questions, I'll try to answer them.
I see a question in the Zoom. So the question is, what are the stripes around the cube?
This is still the cup. So it's a piece of, I'll show it. So this was a coffee cup. And that was the stripes that you could see around the cube. So it was, the cube is just at the bottom of the coffee cup.
Okay, thank you very much for the questions, and also thank you very much for the presentation, for this very live laboratory.
At least you could see how a live laboratory works.
It's a real. We are really with you in your basement, in your the laboratory there. We are now 5:15. I don't know whether, David, you see whether there are some questions which were sent to you directly here in the here.
I think I answered. I answered all the questions. I don't see any more.
Okay, good. So good. Thank you very much again. And now it's time for just getting ready for the quiz. We immediately jump into the quiz. Yeah, give you some time to get ready. So Mattia sent you a link to the quiz.
Yeah, so you can register from now, and I'm waiting you on the other side. I can start also sharing my screen.
Okay, Mattia, your microphone, your voice is very low.
Now better?
Now it's a bit better, yes.
Okay, so now can you start registering to the quiz? I'm just starting to share the screen so everyone can see it. Okay, I'm waiting for you here. And I'm waiting for the participants.
Okay, just shout, participants, if there's a problem, if you cannot raise it, so just let us know.
Okay. Oh, there are already a lot of people. Let me see, how much are you?
Sorry, but we can't get in.
Mattia, you always have...
Sorry, just one question. I don't see. You have problem for access from the link?
But we can't register.
And why? What's the problem? What will you see in your screen? I can stop sharing for now. Just 1 second. So Atomic Earth Mother resolved. Who's missing?
Mattia, can you see the chat? MNP says you should refresh the site. Is this possible?
Yeah. I don't know who were speaking before. So who weren't enabled to log in. I didn't see.
I don't know. Was it Atomic Heart Mother? You had problems, but somebody else?
Mattia, we will have 17, not 18, 17 groups.
Yeah, thank you. Thank
One
you.
is missing.
Yes, and now I'm actually counting too much participants because I'm counting actually 19 participants. So I don't know if there are someone from a team that it's in a different location, in different places, but I ask you to participate only one and to share the screen with your teammates, because and chat each other. I can reshare my screen. Just 1 second. Okay, so you are basically all here, but we have a 19 participant and I cannot see who is exceeding. I'm sorry. But anyway, we can play like that, and then I'll try. If I see people from the same team, I'll calculate an average for you. I don't know if you're from separate devices, and we can calculate an average for your team.
Mattia, can you see the team names? Maybe I should go through this. And
I can see only that there are 19 participants, and no, really I cannot.
Yes, it is too much. We have 17.
Yeah, exactly. I don't know, maybe here.
Sorry, I've got only one question for my team. Are we going to see on Zoom questions or inside of this app?
No, I suggest you to play on the app following the link. I'm sharing the screen just for people that are in separate
Okay,
place.
thank you.
Okay, I think it's faster and easier for you as well. So, okay, now we are even 20. Okay, let's
More
see.
and more.
Maybe official results will be ready tomorrow morning, and I'll send you by mail if there are some gaps. Okay, so we are exceeding, so I think we can also start. And
yeah, just a quick question whether to the teams, whether everybody is ready. Last occasion to shout out if you're not ready yet. 1, 2, 3. Okay, Mattia, go ahead. I think everybody's ready.
So the quiz is starting. Just now she'll start the countdown for the first question. It's a close answer question, and the question is, who discovered radioactivity? You have 15 seconds to reply. Okay, great. Not bad at all. Congratulations. And then the next question. The second question is, just a second. Okay, it's coming. What is fission? So everyone has voted. In the end, we have 17 participants, so everything seems to be seems to be going well here. Okay, great. Let's go to the third question. The third question is, what is a chain reaction in our context? Okay, almost everyone has replied. Yes. The correct answer is the first one. Then let's see the next question, the fourth, which is, why fission does not produce CO2? Last second. Okay, great. Again, 9 correct answers. Then the fifth question is, what is roughly the weight of a fuel needed for 1000 megawatt electric for 3-4 years in a fission nuclear reactor? Professor Ambrosini explained today very well. And yeah, you got it. Great. And then the last question, it's a bit longer, so you'll have 5 seconds more, 20 seconds to answer the last question. Let's move on. Okay. What is the main message in the recent report from the European Commission Joint Research Center about the do not significant harm issue in relation to nuclear energy? There's still time. Everyone has voted, great. Yes, 9 correct answer. And now let's see the results for this first quiz for today, for the second day of the nuclear competition. It's calculating. And the winner for today is the nuclear squad. Congratulations, you won the first quiz of the nuclear competition. You have been the fastest and you gave the best solution to most of the questions. Congratulations again. So for today, the quiz is over, and we will have 2 more quiz tomorrow and the day after tomorrow. Thank you all.
Okay, thanks a lot, Mattia. Okay, you stopped sharing. Question to all of you, can you give me some feedback? Was this quiz okay for you? I have to confess that my quality here on my screen was quite bad, but how was it for you?
It was same here.
It was everywhere very bad, the picture.
Okay.
But even for participants that joined from the link, this is the main question, because if the participant can correctly join the link and see on their screen, they shouldn't have any problem related to quality and so on. So I would ask also to participants to join directly the link if they had any problem.
Yes, because otherwise we cannot read it.
Yeah, and I imagine, unfortunately, sharing the screen, it's not always the best option, but for teams that join from the link, I hope everything went through.
Mattia, excuse me, we cannot hear you. We always have the problem with your...
Yeah, sorry. I said I hope that for participants joining from the link, there has been any problem in terms of quality and connection. So I don't know if there could be some feedback from people who joined the link I sent.
There is enough time to read the answers and then choose.
Okay.
There is not enough time to read the answers, so maybe then tomorrow we'll make
yeah, sure,
a longer response time.
Okay.
The questions are not hard, but it's not enough time to see the whole questions and
quickly
find the answer.
Okay. So you prefer maybe 20 seconds for each question? Could it be better? Like for the last one with
maybe 25.
25, yeah. Okay.
Okay, let's discuss. Great. So let's discuss the. Well, we always do a feedback after each day. So let's discuss the timing for the questions, and also let's check out the quality on the screen. I think it's here on the main screen. I don't know whether it was an issue for everybody, but for some people it seemed to be an issue that the quality of the picture wasn't so good. But I think it wasn't a problem on the app. It was only a problem if you read the question on the screen. Okay, so, well, congratulations again to Nuclear Squad. Where are you, by the way? Can you show your picture? Let us upload.
I don't have my camera plugged in, but we are here.
Okay, so it's Christoph or?
Yes.
Okay, so big applause to Christoph and his team. Let's give it an applause. Yes.
Thank you.
Okay, so tomorrow, new game, new luck. Hope to see you again tomorrow, and yeah, hope you found it a bit interesting today. And now tomorrow, so we have 4 new teams, and I'm already looking very much forward to all your videos and all your presentations. Okay, see you tomorrow. Bye.
Bye.
Bye. Bye. Thank you.
Bye.